So the first part of the notes is going to be the kinetics, like I said, and then Monday, we'll do the equilibrium portion. So when we're talking about the reaction process, our journal question today was, why are some reactions slow and some reactions fast? And this is going to talk a little bit about that. So, of course, if you look at these examples for the rusting of iron or burning, rust takes a long time to happen. It's a very slow reaction, whereas burning things is a very, very fast reaction. And that is what kinetics is about. It's studying the rates of reactions and why some things are fast and why some things are slow. Okay? Because just because a reaction is favored to be happening, it doesn't mean it's necessarily going to favor to be happening quickly. Reaction rates take into consideration how fast or slow, and we call this the rate of reaction. Also, sometimes we refer to those as rate laws. And what is telling you is the rate either of the disappearance of the reactants or the rate of the appearance of the product, depending on which one is easiest to observe. So some reactions it would be easier to observe how fast the reactants are disappearing, and others it would be how quickly are the products appearing. The units are m per second, which is molarity, of course, per second. So that's what the rate of reaction is. The reaction rate causes, in other words, why do reactions even happen? There are some conditions that have to be met for them to even happen. And the first one is the number of collisions, so total number of collisions of the particles. If you don't have enough collisions, you won't have a reaction. The other thing, the next one is orientation of the particles. If you do not have a proper orientation when the particles collide, there will be no reaction. In other words, if I had, say, an ionic compound trying to react with each other, if the two negative sides bumped into each other, would they react? No, because they would repel, right? Because the two negative sides. They have to have the correct orientation of the particles. And then you need to have a collision with enough energy or sufficient energy. Okay? Together, this is all called the collision theory. So you might want to draw yourself like a little line like that and write collision theory. These are the parts of that. Okay? You got to have enough particles colliding. They have to have the correct orientation, and they have to have sufficient energy. When all of these conditions are met, we refer to those as effective collisions. Okay, any questions on that? Okay, so let's talk about the energy portion of it in a second. Okay, this is just a visual to kind of show you why some collisions are not effective. So sometimes they're moving too slowly, sometimes they're not facing the right way, but then when all three of these conditions are met correctly, then you have effective collisions and you get a chemical reaction. Here's another example of not being oriented properly so that no product would form unless it was oriented in the correct way. So let's talk about the potential energy. You have this diagram in your notes. These are the potential energy diagrams, and what they represent is they represent the energy pathway of the reaction. Okay, so at the top of this hill, the energy hill, is something called the activated complex, which is one of your vocab words that you will have to know. It's the activated complex. Okay, and that is at the very top, right there and right there. That is the activated complex. And at that point, what's happening is you actually have bonds breaking and forming. So like your reactant bonds would be breaking, but your product bonds would be forming. So both are going on. So it's going to be different than what the final product is and different from what you started out with. Okay. The energy required to form that activated complex is called the activation energy. And the activation energy, if you look, is the difference between the reactants, the energy of the reactants, and the top of that activated complex. That's your activation energy. If you notice on the exothermic, it is less than it is for endothermic. Endothermic reactants are down here, and it requires more activation energy to be able to make that activated complex. And so make sure you make note that this one was endothermic and energy is being released. And when energy is released, our delta H, who remembers what the value is for exothermic? Positive or negative? Negative. Yeah. Yeah. And then for delta H for an endothermic is the process of positive. Okay? And that's because energy is required or absorbed during the endothermic process, so that delta H would be positive. Okay? Does everybody have that before I move on? This is just a bigger diagram. I actually forgot it was there. I could have drawn on that one a lot easier. Remember, the top here is your activated complex. If you didn't label that on your graph, you should. This was the activated complex at the top. Same thing here. And then, of course, this difference here is your activation energy. We usually label that as EA right here. And that is how we show activation energy. Okay? So the factors that affect the reaction rate are some of the things that we talked about when we did solutions. Some of those same things are going to show up because the solution process is affected by some things with kinetics as well. First one we're going to talk about is the nature of the reactants. So first thing is if it's how reactive is that particular reactant. So reactivity. So obviously if I was talking about, say, a noble gas, it has a very low reactivity, so it would very much affect the reaction rate. Okay? But if I was talking a group 1 metal, which is the alkali metals, which are the most active metals there are, the reaction rate would be much, much quicker. Okay? Ionic reactants occur pretty much almost instantaneously, and that's because you don't need the electrons to rearrange. They've already transferred. So since the electrons already are transferred, the reaction happens very quickly because you're not having to figure out who's going to share or where's it going to go. Okay? If it is a molecular reactant, and molecular means same thing as covalent, okay, it's going to occur more slowly because you're having to rearrange the electrons. Okay, so these are very fast, and the molecular are a lot slower. Everybody have that? Temperature also affects the rate. If I increase the temperature, I increase the energy of the collisions. Okay, and because I am increasing the speed of the particles. And so when I increase the speed of the particles, remember we talked about that, kinetic energy is directly related to temperature. So if I increase the temperature, I'm increasing the kinetic energy. So the particles, excuse me, are moving faster. So they would have more kinetic energy. Okay? When we talked about those graphs a while ago, remember it takes energy to break the bonds, which is endothermic, and energy is released when the new bonds form, and so it would be exothermic. So breaking the bonds is endothermic, forming the bonds is exothermic. So you don't have this graph in your notes, but I just wanted you to look at it when we talk about increasing the temperature. The shaded area down here is the particles that had enough energy to form. Okay, so when I have a lower temperature, notice the number of particles is way down here. But when I increase the temperature, because my particles are moving faster and have more energy, I get a lot more particles up here that were able to have that minimum kinetic energy to overcome the activation energy. So that's why higher temperature works. When we're talking about surface area, we talked about this when we did solutions. Remember, heat it, crush it, stir it. The crushing it makes it have smaller pieces, but it gives it a larger surface area. And of course, that causes increased collisions because there's some more particles available to collide. Stirring it or agitating it has the same effect because what it's doing is it's removing reactant particles very quickly. What you're always looking for when you're doing that is you want fresh solute to solvent interaction. So if I have fresh particle interaction, then it's going to react faster. Okay? So those have that same effect, kind of. We're constantly introducing the reactants to each other that haven't already reacted. And so this is just kind of show you, like if I had a sugar crystal, you know, sugar crystal, only the outside layer would be reacting. And so only this part would actually be reacting. But if I start breaking it up into smaller and smaller pieces, now I have more particles that are ready to interact. And so that rate would be increased. It would happen faster. For some reason, when I say large surface area, people get confused that means smaller particles. So just make sure you understand that the smaller the particle, the larger your surface area is. A real fine powder is going to react a lot quicker than a big chunk. Presence of a catalyst. Our video talked about this. Remember, a catalyst is something that increases the rate of the reaction without being used up. So you need to underline that. It is not permanently changed or used up in the reaction. The way it works is that it actually provides an alternate pathway that has a lower activation energy. Okay, than the original. The video talked about the catalyst in the reaction. A lot of chemical plants use catalyst, and what happens is as the catalysts are used for a while, they get kind of dirty or they get a coating on it, and so they remove the catalyst and they send it out to be cleaned. Okay, it's called spent catalyst. They send it out and they get it all cleaned up, and then they reuse it because they can use it more times than once. That's important because some of these catalysts are very, very expensive. They mentioned in the video platinum and rhodium and palladium. Those are very expensive metals. They're way more expensive than gold. Okay, so they want to reuse that. Okay, the plant that my husband used to work at used rhodium catalyst, and one time they had a truck that was delivering it to be cleaned, and the truck had an accident and spilled some of the catalyst. They were literally out on the side of the road trying to pick up all the catalyst they could because the rhodium is very expensive. And it's not readily abundant. It's not like there's a huge supply of it like there is, silver. Okay. In our bodies, you know this. What are our catalysts called in our bodies? Enzymes. And you have so many enzymes working in your body. I couldn't even begin to tell you how many. Digestion is an important example of enzymes. Digestion on its own would take years, but because we have enzymes in our body, we do it in a matter of hours. Okay. Alternatively, it's basically the exact opposite of a catalyst. We have something called an inhibitor. And it is exactly the opposite. Instead of increasing the rate, it decreases it, and it forms a new pathway that has a higher activation energy. So it tries to slow down the reaction. And preservatives are a good example of that. We put preservatives in our food to inhibit the decomposition process of your food so it doesn't mold as quickly. And you have this graph, and we're going to add the inhibitor on it, but if you look at the blue, that is what the activation energy is without the catalyst. And what I want you to notice is that the reactants and the product's energy stays the same when something's been catalyzed. That part doesn't change. It just lowers this activation energy. It helps us get there quicker is basically what it does, okay? Because it doesn't take as much energy to overcome it. But the amount of energy that it starts and ends with remains the same. If it was an inhibitor, it would look like this. It would come up and raise that. So draw that on there and write inhibitor. And of course, we already talked about the examples of an inhibitor, or examples of that's in your notes as well. So concentration of reactions makes total common sense that if I increase the concentration of my reactants, they will cause there to be more collisions. When there's more collisions, you have a better chance of them being properly oriented and a better chance of them having enough energy to overcome the activation energy. So increasing the concentration helps. When you're talking about gases, increasing the pressure has the same effect of increasing the concentration. Because remember, when I increase the pressure, the volume goes down. And so now I would have the same amount of particles, but in a smaller volume, so that would effectively be increasing the concentration. So that's how it works for gases. So here's an example. The more concentration you have, the more particles you have to collide. So in this case, it would be a very low in the first one because you don't have very many particles. But in the second one, it would be higher because you have more particles to react. The reaction mechanism, this is almost the last thing we're doing for today. Whenever you see a balanced equation, you're actually only seeing the overall equation. Okay? You're not actually seeing what happens in between. Because when it comes to doing the stoichiometry or figuring out how much product we can make, we only care about the overall reaction. But in fact, it actually usually takes several steps. Okay? And that's what reaction or kinetics is. Okay? And we can determine the rate laws of these things as well, but we're not going to do that. We don't have to do that in here. So in this particular one, you have this in your notes. Draw a line under A through D, and that is your overall net equation or overall net reaction. So that's what's actually happening. If we were to do some stoichiometry with that, we would care about A going to D. We would care about the stoichiometry of that. But in fact, it's actually a three-step process. So actually, A forms B, and then B forms C, and then C forms D. But they're used up in subsequent steps. So we would cross those out because they appear on both sides of the equation. And B and C are called intermediates, which is one of your vocab words. Forgot the S. The S doesn't fit on there. And they are formed and then used up in a subsequent reaction. So they don't appear in the overall reaction. But they're important to the process. If you don't form the intermediates, the reaction won't proceed. Okay? So here is an example with real stuff instead of A's and B's. Okay? So in this case, these are your intermediates because they're formed and then they're used up. So those would be your intermediates. Okay? These steps, 1, 2, and 3, are called steps in the mechanism. The whole thing is the reaction mechanism. And then the bottom would be our overall net reaction, what actually starting and ending with. Okay? Now, usually one of those steps is a rate determining step. Okay? Meaning how quickly or how slowly the reaction proceeds. The rate determining step is always the slowest step. Oops, I did that wrong. Sorry. It's supposed to be rate determining. Kind of like, you know how they say you're only as strong as your weakest link. A chain is only as strong as its weakest link. A reaction is only as fast as its slowest step. Okay? And then there's going to be 2 definitions that I'm going to need you to add in that got left out of the packet. And so that's going to be on the next slide, but I'll wait till you have all that. I got that? Okay. There can be more than one reaction pathway. That is just one. There's other ones, but overall we care about the overall net, and of course the things in the middle we call the intermediates, which is a vocab, so make sure you know that. You're going to need to add these definitions to your notes. When we're talking about this, a reaction that has all of its reactants and products in the same phase are called homogeneous reactions. Okay, so this is an example down here, gas, gas, gas. This would be a homogeneous reaction. And then conversely, if it has two different phases, we call that a heterogeneous reaction. And that is definitely a definition that you need on a test. That's why I had to make sure you added it in. Okay? Does everybody have that, or are you still writing?
Still writing.
Okay. Is everybody good? All right, that's where we're ending.